Simplify the square root of 36 over 49. So what I've done is written perfect squares above. Square root of 1 is 1, square root of 4 is 2, etc. So when we're simplifying, we can rewrite this as two separate radicals. The square root of 36 over the square root of 49. Now we know that the square root of 36 is 6, and the square root of 49 is 7. So our answer would be 6 over 7. Evaluate the following: the square root of negative 100 and the opposite of the square root of 36. So when we're talking about even roots, square roots, fourth roots, sixth roots, etc., our radicand, the value underneath the radical sign, cannot be negative. Because let's talk about square roots for a second. Square root means what value multiplied times itself gives you the radicand. You can't multiply a number times itself to get a negative value. So for this, there's no solution. Now, it's okay if the negative is on the outside, because what this is asking us when it says the opposite of the square root of 36 is we know our answer is going to be negative, and we're looking for the value multiplied times itself that gives you 36, and that would be 6. So our answer for this particular problem is negative 6. Okay, the next problem says find the domain of the function g of x equals the square root of x minus 9. So as I just said, the value underneath the radical sign, which we call the radicand, cannot be negative. So how do we say that in terms of symbols? We say the radicand, which in this case is x minus 9, has to be greater than or equal to 0. So we go ahead and solve. Add 9 to both sides, and it gives us the statement x has to be greater than or equal to positive 9. So if the values of x are greater than or equal to 9 and we plug it in for x, the value underneath the radical sign will not be negative. So how do we state that in interval notation? So we look at our number line, and our number line goes from negative infinity to positive infinity, and our boundary point for this problem is 9. So the statement is the values of x are greater than, so that would be to the right of 9 on the number line, or equal to. So when we're using interval notation, remember we use a bracket to indicate that that point is included in our solution. So in interval notation, we look at our number line. The point furthest left is 9. And since our graph continues on forever, the point furthest right is infinity. So infinity, remember, gets the parenthesis. And 9, since it's included, gets the bracket. So in interval notation, we have bracket 9 comma infinity and then parentheses. So again, to find the domain, we set our radicand greater than or equal to 0 and solve. So the next problem was similar to our first example. Simplify the square root of 64 over 16. So we can reduce before we simplify. So there is a value that goes into both 64 and 16, and that would be 16. So I'm going to divide 16 out of both of these before I start. So 64 divided by 16 is 4. So that's still underneath the radical sign. And 16 divided by 16, of course, is 1. And that's still underneath the radical sign. Now we simplify. The square root of 4 is 2. And the square root of 1 is 1. And remember, anything over 1 is the value, in this case, 2. Our next problem, again, is to evaluate. And the first one is the opposite of the square root of 4. So we're okay since the negative is on the outside. And the second one is the opposite of the square root of negative 64. So for the first one, the opposite of the square root of 4, remember our answer is going to be negative. And we know the square root of 4 is 2, so our answer will be negative 2. For the second one, since we're dealing with an even root, square root, remember our radicand cannot be negative, so there'd be no solution. So the next problem, it says evaluate the following, the opposite of the square root of 5 to the 4th. And the second one is the square root of negative 2 squared. So what we do in simplifying, if it's broken down into exponential form, as long as when we raise 5 to the 4th power it doesn't give us a negative number, we simplify like this. So we have the opposite, and underneath the radical, 5 to the 4th. So essentially all we're doing, since our root is square root, we'll be dividing our exponent by 2. So that would give us the opposite, and 2 goes into 4 2 times, so on the outside we'd have 5 to the 2nd power. So our answer would be negative 25. So again, we get this exponent 2 by dividing the exponent inside by 2 because we're talking about square root. So our answer would be negative 25. For our next one, we have the square root of the quantity negative 2 squared. Well, negative 2 squared is 4. So we're essentially simplifying the square root of 4, which is 2. In our next problem, it asks us to simplify the square root of y to the 16th. So again, since we're dealing with square root and we're dealing with an exponent of 16, we're dividing that exponent by 2. So 16 divided by 2 is 8. So our answer to this problem would be y to the 8th power. The next example, simplify the square root of 36y to the 6th. So we know that 36 is a perfect square. So we're going to look at simplifying this as 36 times y to the 6th because we're going to simplify each one individually. So we know that the square root of 36 is 6. And again, when we're looking at something in exponential notation, since we're dealing with square root, we divide 6 by 2, and that gives us 3. So our answer would be 6y to the 3rd power. Next, we're asked to find the value of the cube root of negative 27. So since our index, which is this value here, which is our root, is odd, we can have a negative underneath the radical sign. So what we're going to do is break down negative 27. So negative 27 can be rewritten as negative 3 times negative 3 times negative 3. So underneath the radical, I have the cube root of negative 3 to the third power. Because I have 1, 2, 3. Now we're going to use that same principle as we just did with things in exponential notation. We're going to divide our index into our exponent. So 3 goes into 3 one time, so our answer would be negative 3 to the first power. And negative 3 to the first power is negative 3. So we're dividing our index into the exponent. And notice when we do that, it comes outside of our radical. Our next two examples, we have the fourth root of negative 625 and the opposite of the cube root of 64. So keep in mind again, if our index is even, square root, fourth root, sixth root, etc., our radicand cannot be negative. So in this case, there'd be no solution. For the second one, we have the opposite of the cube root of 64. So 64 can be rewritten as 4 times 4 times 4. So we have the opposite of the cube root of 4 to the third power. So now again, we do our division. So we'd have the opposite, and then our index 3 divides into our exponent 3 one time. So we know 4 to the first power is 4. So our answer would be negative 4. So our next problem deals with another root. In this case, we're dealing with the fourth root of 1 over 256. So remember, we can separate this into two radicals, the fourth root of 1 and the fourth root of 256. So we know that the fourth root of 1 is 1, because 1 times 1 times 1 times 1 gives us 1. So 256 can be broken down into 4 to the fourth power. So our numerator is 1. And now in dealing with the denominator, remember we're dividing the root into the exponent. So 4 goes into 4 one time. And we know 4 to the first power is 4. So our answer would be 1/4. Next, we're dealing with the fourth root of 256 u to the 16th. So remember, we're going to deal with these two factors individually. So we have the fourth root of 256 times u to the 16th. So again, we're going to break down our coefficient. 256 we can rewrite as 4 to the 4th power. And we have the u to the 16th as well. So since we have this in exponential form, I can divide my index into each of these exponents individually. So when I divide 4 into the exponent 4, that gives me 1. So I have 4 to the 1st on the outside. And when I divide 4 into 16, that gives me 4. So 4 to the 1st power is 4. And I have my u to the 4th. So now we're going to revisit domain again. And here we're asked to find the domain of the function f of x equals the square root of x plus 1. So the plus 1's on the outside of the radical. So the restriction to this problem is just the radicand. Remember, the value underneath the square root cannot be negative. So we always set the radicand greater than or equal to 0, which means not negative, and then we solve. Well, this is already solved for us. So our domain would be the values of x that are greater than or equal to 0. So to put it in interval notation, our number line goes from negative infinity to positive infinity. Our boundary point is 0, and the values of x are greater than to the right or equal to. Remember, when it's or equal to, we use a bracket. So in interval notation, our point furthest left is 0, and that has a bracket, comma, our point furthest right, since it continues on forever, it continues to positive infinity, and infinities, remember, always get the parentheses. So our domain would be all the x values that are greater than or equal to 0, and in interval notation, bracket 0, comma, infinity, and we end that with a parenthesis.